Okay, so I recorded this in third hour, and then I like went through everything, like did all of it, and then I looked down, and it recorded for like a minute, and I was like, it's all gone. I am. Third hour would be like, I remember that, and seventh hour is gonna be like, what just happened? So first off, we want to take and just get all of the equations up here. I'd suggest taking them down for yourself so you have them. I'll also post these notes online, plus this video will go up online. So that's nice too. You can get them multiple places. But we've got Hooke's law. The spring force is Kx. Remember, this is a spring constant. And this force, you can either use, it gave you a force, but often if you have a vertical spring, mass times gravity. If a problem says that a mass is hooked onto a spring and then it is gently lowered to a new equilibrium position that is some distance lower than it was to start with, that force is going to be the force of gravity on that object. Beyond that, we've also got kinetic energy as 1/2 mv squared and potential energy as 1/2 kx squared. These two k's are the same thing. Where is it? There it is. Those two k's are the exact same. So a problem might have you find the k using potential energy and then find the force afterwards. It could be like a two-step problem, one then the other. Or you might have to use the force and the distance that's been stretched to find k to then get potential energy after that. Both of those are fair game. But together, total mechanical energy is kinetic energy plus potential energy. At any point during some oscillation, your object's moving back and forth, you got a spring going, the total mechanical energy stays the same. And that's useful for a couple of different points. Our total mechanical energy is equal to our potential energy at what points? Where do we have all potential energy? Peaks and troughs. So if a problem's asking about either a peak or a trough, you can set this up. So this is at peaks and troughs. I don't like the word troughs. Valley. Valley. It's like Blue Valley or something. Which is pretty cool, not gonna lie. We're golfing now. So, our total mechanical energy is equal to our kinetic energy where at? Equilibrium position. So, at equilibrium, that is true. One of the things that you might be required to do, and number 6 on that review sheet we just got is this way. Ultimately, number 6, if you take a look there, it's asking about velocity, which is kinetic energy. And it's asking about the equilibrium, so we know that our total mechanical energy, whatever it is, can be set equal to kinetic energy. I was just like, all right, I'll do kinetic energy equals 1/2 mv squared. I'll just plug in all my information. I'll solve it. It'll be great, nice and easy. It gave me a bunch of extra information, but who cares? That's just stupid. But it didn't actually tell me how much kinetic energy I had at that point. At the equilibrium, it didn't tell me that, but it told me a lot of other information about potential energy. So I'm going to get some of those points up there. Number 6. Yeah, it says that we've got a spring constant of 200 newtons per meter. We've got a mass of 0.75. And we've got a distance stretched. Our amplitude is 0.5 meters. We don't have enough information to go straight into 1/2 mv squared. We've only got mass. We don't have the actual amount of energy, but we do have enough to go into potential energy first. That x is at our peak or at our trough, right? It says that it was stretched that far. That is our x. So we can say that our potential energy is equal to 1/2 kx squared. that is also equal to our total mechanical energy because we're at a peak. Because our X value that we're using is for a peak, that makes it the total mechanical energy as opposed to just some amount of potential energy it has anywhere. So when I solve that, 0.25 times 200 is 50 times half. Our potential energy, which here is the exact same as our total mechanical energy, equals 25 joules. So that tells me a lot more information about every other point that this object goes through. Finding your total mechanical energy if you are stuck is the best thing you can possibly do. If you're stuck with a problem with energy, find your total mechanical energy first. From here, I know that it's asking me for my velocity at equilibrium. And at equilibrium, you guys just told me that we have just kinetic energy. So that total mechanical energy that I solved for is equal to just kinetic energy, which is 1/2 m v squared. And now I can just solve for my velocity. Both sides by 2, I get 50, divide it by 0.75. Oh, is it just 0.5? Sorry. No. The mass? Oh, I must be on some different problem. Sorry. Sorry about that, YouTube. Oops. That's the problem. This is like fully candid. When I was using the iPad app, it was like super easy to just stop, rewind, and re-record over something. Now this is just full stream of consciousness. Like there's no, I'm not going to go back and edit this. That's ridiculous. So if you're watching this, hope you enjoyed that little sidebar. Now back to physics. Brought to you by NPR. And this comes out to be, divide it, 100, square root of it is 10 meters per second. That's right. That's a good indication of the level of thinking that a question or a series of questions would go through. One question might first ask you to find the potential energy at the amplitude. Then it might ask you, what's the total mechanical energy? And if you solve for one, you already got it, right? Then it might ask you for the velocity after that. That could be 3 questions, 3 multiple choice questions out of that one. Beyond that, we also do have, I'll go to the next slide, these 2 equations. The period of a spring is 2 pi times the square root of m over k, and the period of a pendulum is 2 pi square root of L over G. One of the things to be extremely careful about, and I realize this in most of the calculators, when you type this in for the first time, if you are going to divide both sides by 2 pi, if you're going to divide by 2 pi, make sure that the 2 pi is in parentheses. If you just type in, so that your calculator read out like whatever your t was, let's say it was 5, divided by this, if it was written out just like that in your calculator, what it's doing is taking 5 divided by 2 and then multiplying it by pi, which is not what you want. Either do it as 2 separate steps and do, divide by 2, divide by pi, or make sure you put those parentheses. If I change, let's say I had a spring, like this guy, and it had some period, let's say it was 5 seconds, and I took it to the moon. Is that going to change the period of the spring at all? No. There is no acceleration due to gravity in my spring equation. The only things that affect how fast the spring oscillates is how stretchy the spring is and what mass is on it. If I take it to the moon, no effect. Like it's the exact same thing. That's how they actually get people's masses on the moon when they're out in 0 gravity, because scales don't work. But for a pendulum, it does. If we go to, the moon with less gravity, we actually have a longer period. by what factor would I have to decrease my gravity to get my period to double? 2, 16, 107. Think about this like we've done. So really what we have to do is get this side of the equation to get twice as big. So if I'm going to add some, or actually twice as small, if I'm going to add some number in here to get it to be 2 times as big, what does it have to be?
Like 4 times the length.
You could do 4 times the length. If I did 4 times the length, that would mean my period was 4 times. I'm sorry, it would be 2 times. What I'm trying to say here is that if you want to, if I double the length, the effect on the period is 1.414, the square root of 2, more than it was before. Just like when we had this equation, F equals big G M1 M2 over R squared. And if we doubled the radius, we had a change of 4 times. 4 times smaller, but 4 times because we had to square it. The same thing is true here, but now that has to get square rooted. So if I double the mass of a spring system, I only get the square root of 2 longer of a period. If we took a look at back here with this equation for the potential energy, if I double how far I stretch a spring, I get 4 times as much energy because that x gets squared. I think there's a couple problems on there that deal with it. Number 11. Let's take a look at number 11 real quick on the review. So the spring is compressed and released so that it has a total mechanical energy of 20 joules, right? Its baseline, what it normally does is 20 joules of total mechanical energy. But if I compress it 3 times as far, that means I'm going to get some different amount of joules. So what I'm going to do is, I said that I had 1/2 kx squared, right? After I compress it 3 times further, does my 1/2 change at all? No, doesn't. The 1/2 is still 1/2, so I put a 1. Just because I compressed my spring further, did that change how stiff the spring was? No, the spring is what the spring is. But I did compress it 3 times farther. I've displaced it 3 times farther than it was. And when I do all that, I get 9. What that means is that I am now 9 times what it started out. My potential energy now, by compressing it 3 times further, is 9 times bigger of an energy. So the answer there should be 180 joules. You could do the same thing with one of those pendulum problems, where we've got inside the square root. Make sure that you know what affects springs versus what affects pendulums. There's a couple questions that pretty much say, hey, we take it to the moon. Did it change the spring? Yes or no? Did it change the pendulum? Yes or no? And then did it increase it or decrease it? If this number gets bigger, if there's more gravity or the spring constant is larger, your period is smaller. If the top number gets larger, if we have a longer pendulum or more mass, your period gets longer.
You said you were compressing it, right? So
Yes.
how come the x gets 3 times larger if you...
Because we're getting 3 times further away from that equilibrium position. So if I stretch it, it's whatever this distance was, I make it 3 times bigger. But if I'm compressing it, I'm still getting further away from that equilibrium position. Our x is always how far we are from the equilibrium. Okay? That was Nick Folkers, ladies and gentlemen, getting interviewed on Physics Talk with Merlin Bach. That's it. Physics Talk with Merlin Bach. That kind of half rhymes, maybe. We're doing it. I'll be on Twitch. I'll stream on Saturdays from 1 a.m. to 4 a.m.
I'll be up.
I won't. I'm in bed by like 11,
Nick and I will be.
doing whatever. Let me take a look. Let's take a look at some of these graphs. Again, this graph right here. Let's say this is 2, 4, 6, 8, 10. A graph like this, there will be, I believe, 13 questions based around this graph. First question for you. What's the period of oscillation? It is 8. We go peak to peak or trough to trough. If we look down here, and if this graph extended out, this would hit a trough again at 12 seconds. We would go 4 to 12, or we can go 0 to 8. If it starts at the equilibrium, just remember that you have to go through 2 equilibriums to get there. We have to go through a whole range of motion. The period is the time to go through a full range of motion. If we just stop at 6, that's only half. We haven't gone up at all. So we said the period is 8. What's the amplitude if this is -4 and this is 4? Just 4, yeah. Our amplitude is the distance from the equilibrium position to that highest point or down to that lowest point. It is not the entire thing. It's not 8. It's just from the equilibrium to the highest or down from the equilibrium to the lowest. What's the frequency?
Isn't that just the inverse of
It is the inverse of the period. Frequency is 1 over the period. So 1/8 for this one. Means we go through 1/8 of a cycle a second. When we get into like light and sound waves, we are going to be working with much higher frequency deals than this. But remember, the unit is hertz, capital H, lowercase z there. Stuff that can be asked from here. I'll grab my sheet of paper. Oh, that's right. That's where I want to go. Where do we have our greatest velocity? At what times do we have our greatest velocity? I heard whispers. What?
2, 6.
Whenever it hits the equilibrium, we have our greatest velocity. So velocity is greatest at time 2 and time 6. Which one of these is our greatest positive, and which one of these is our greatest negative velocities? What's the velocity of a position time graph? How do you get it? Slope. Anybody in calculus? Couple people. For you couple folks, these are derivatives of sine. You get them? Good. So our velocity here, because our slope is negative, it's on its way down. This is our greatest negative velocity, and this is our greatest positive velocity at 6 seconds. Draw little arrows there so we can see those. And we've got velocities of 0 up at the peaks and troughs. So a question will likely ask you to pick out times, say the time of 2 seconds, not just know that it's at the equilibrium, but then look at the graph and say, all right, there's an equilibrium at 2 seconds and there's one at 6 seconds, or 3 seconds, or 7 seconds, or whatever that graph shows. Where are our accelerations the greatest? Or where are our forces the greatest at? Who did I pull a string against in this class? Is it Will? So, Will, I know it's probably like the fifth time I've asked this, but as we pulled farther and farther out, did the force get bigger or smaller? What's that? It wants to go to the equilibrium, so the force always points towards the equilibrium. But as we pulled farther, did it get harder or easier to hold on? Harder. Got harder. So as we are farther out, as we are more displaced from our equilibrium, there is a greater force being applied by that spring. So our force is greatest at peaks and troughs. But like Will said, he said it wants to go back to the equilibrium. So if we are at the top, we've got our greatest downward force. It wants to go back down to the equilibrium. And if we are at the bottom, we want to go back up. We have our greatest positive force, which translate to be greatest, upwards and downwards accelerations as well. Whatever is happening to the force, the same can be said about acceleration. Net force equals ma from there. Where do we have the greatest potential energy? Where's our greatest potential energy at? What's that? Peaks and troughs. So up here, we've got potential energy at the max, and here we've got kinetic energy max. We've said that a couple times already, but it comes up again and again and again and again. And remember, it's at any peak or trough for potential energy to be at the maximum, and it is at every single equilibrium that our kinetic energy is at its max. Where is our total mechanical energy the greatest at? Where's total mechanical energy going to be the biggest? Same. All the way through. Your total mechanical energy is the same. There are problems we could do where we change total mechanical energy, but we're not going to. For all of these, total mechanical energy is the same throughout. Throughout. I can spell good. Remember that the distance traveled in one period is equal to 4 times the amplitude. From this point at the beginning to the equilibrium, we went a distance of an amplitude. Then again, from here down to the bottom, we went another amplitude. From the bottom up, that's another amplitude. And from the middle, from that equilibrium to the peak, that is a 4th amplitude. That is true of every single one of these. Whether it starts at the equilibrium, starts at the bottom, starts at the top. That picture is very messy. Incredibly. The last type of graph, or was somebody still, sorry, I jumped the gun there. I think we're all good. All right, the last type of graph we had, how much time do I got left? 2 minutes, 3 minutes? No, that's not true. 104? I got like 6 minutes, perfect. So, we also had potential energy versus time graphs. These are slightly different. There are four questions based on one of these graphs. They look like the other ones. They are still sinusoidal waves. But there are important differences. We said that whenever we hit a peak or a trough, we get our total mechanical energy. We get our maximum potential. So we alternate peak, trough, peak, trough. That cannot possibly be correct. There we go. So on this graph, if we were looking at it as if it was a position time graph, we would say, all right, peak to peak, that's our period, 1 second. But this doesn't represent where something is. This represents how much energy it has. So in order to say how far it, or what its period is, we have to really label these and say, all right, peak to peak. It's actually 2 seconds as our period there. Our total mechanical energy is whatever this graph reads at the top. If we're at the peak potential energy, the most potential energy we can have, that's our total mechanical energy. Down here, these are equilibriums. At those points, we have all kinetic energy and 0 potential energy. From here, some of what we do with this problem, we'll be saying, all right, here, or this sort of graph is, say, all right, at the beginning, you're going to have to pull the potential energy off of the graph and then plug it into one of those equations. So if I say it was stretched to an amplitude of 0.5, and this highest point was like 7.3, I would ask, what's the spring constant? Because you know that at the highest point, where you have some information about the amplitude, 7.3 equals 1/2 k, and then that amplitude squared. And then solve it just like you would the others. What I would say is worksheet number 4 is a gigantic part of the test. The other part is going to be the worksheet that you just got today. You are still expected to finish the entire worksheet packet, but if it was me and I was trying to study for the test, I would focus my time on worksheet number 4 and worksheet, the one you got today, the review worksheet. Those will cover everything the best, I would say, the most concisely. Sound good? Soft jazz music plays. This has been Physics with
Papa Josh.
Physics with Fifth Hour.
Papa Josh. No, that's
No.
this is
All right.